Hello, friends. It's your boy, Mr. Stone. Returned from the grave or the apocalypse bunker, as it were. We've got to get back to work. And we're going to start, actually, not with work. We already did that. That's force times distance. Instead, we're going to move on from translational motion. Now, translational motion is what I just did with my hand. It starts here, moves over to the side. It's motion in one dimension. Motion in two dimensions, that is, up and also to the sides, circular, curved motion, is either rotational or angular, just a difference in terminology that doesn't really matter. If I share my screen, hopefully we can begin to take some notes. All right. Okay. So rotational motion is motion that moves through two dimensions. Again, another term for this is angular motion. Contrast this with translational motion, which is what we've done more or less up until this point, except for our brief foray into orbits and centripetal motion. So translational is linear, whereas angular or rotational motion should be relatively apparent why you would also call it angular motion, because there is no angle when you move in a line. I guess unless you have like an outside reference point. But angular motion, you must, or rotational motion must be at an angle because you're moving through two dimensions that angles your line. The easiest way to define angular motion would be to refer to it as motion about or around an axis. The axis being the poles around which the thing turns. Now, if those poles are located inside of the object, that is an internal axis, and we would call that form of angular motion rotation. If the motion is about an external axis, that is to say the center point around which it turns is outside of itself, then we would call that revolution. To rotate is rotation, to revolve is revolution. For an example of each, translational motion would be like taking a particle and moving it through one dimension from an initial to a final position. Angular motion around an internal axis could be something like a toy top. If these are the poles around which it turns, which typically is, then we have an example of rotation around an internal axis. And finally, for an external axis, you can think back to when I had the washer on the string and swung it around about my hand. Or for an example, the lightsaber swinging I also did. My hand, again, being the central point. Now, the question I want to pose to you is, which one of these two does the Earth do? Does it revolve or does it rotate? And of course, this is a trick question. The Earth does both. at the same time. You see, we have our sun. Let's call the center mass point of the Earth-Sun system. The sun very much outweighs us, so it's pretty much just the center of the sun. Let's call that point Q. And the Earth is going around in what is really an elliptical orbit, but of course we can choose to ignore that when we want and approximate it as a circle. Tried to do kind of a 3D thing there. And the Earth is swinging around that point Q. Now, point Q, the center of the Earth-Sun system, is outside of the Earth, so the Earth revolves. Furthermore, you got to keep in mind our axial tilt. Around our poles, which is an internal axis going straight through the Earth does rotate. So there we have rotation around our poles. But the thing is, and I know this is unthinkable for you, but I made a mistake. Of course, like any mistake I do make, it was completely on purpose and justified. One of these drawings is incorrect. One of these drawings is misleading. That is to say, I drew the rotation and the revolution, but one of those is not drawn well. Hang on for a moment. Which one of these is drawn incorrectly? It's actually the revolution. And you can tell from what is called the right-hand rule. You see, when we are talking about the direction of rotational or angular motion, the convention, and of course conventions are arbitrary but useful, clockwise is typically considered negative. Counterclockwise as a direction of rotation is considered positive. A trick to remembering that some people prefer, think of clockwise as CW. Pretend that the C is a negative sign. To have counterclockwise would have two negative signs, giving you a positive. What I much prefer is what's called the right-hand rule. So you take your right hand and put your thumb up. If the thumb of your right hand points up, then your fingers curl in the positive direction. This also is very useful for the Earth. If north is up, your fingers curl in the direction the Earth rotates. And once again, we happen to also go counterclockwise. I just realized I wrote counterwise. Nice. Remember what I said about my mistakes. All on purpose, all completely justified. But anyway, the sun, if you have the sun's north pole as your thumb, then your fingers will curl in the direction of the Earth's revolution. So you can see that we should be rotating and revolving in the same direction. This is not quite right. If the sun's north pole is here, we should be going around the other way. Here. Again, for that right-hand rule, you're going to want to practice that, but...
Sorry, what was that?
Fantastic. Anyway, for the right-hand rule, you're going to want to practice that. You put your thumb up and your fingers will curl in a positive direction. That is the counterclockwise direction. If you want to find the negative direction, of course, you could bend your fingers backwards, or you could use your left negative hand. The units will be different for rotational motion versus translational motion. Because if you are thinking about meters per second or meters per second, then you're going to be kind of confused. Because with angular motion, you have to be going in two directions at the same time. So when I say 2 meters, 2 meters, in which one of the two dimensions in which I must be moving? So instead, we have two options that better describe angular motion. You could either do it by comparing to point Q the difference between this and this position. And of course, that is a change in angle. Or the other option is to describe it by how far along the circle it goes in an amount of time. That is the usefulness of degrees and radians. Degrees we've been using for a long time. Radians you've been using in math and forgetting to change your calculator over all year. This should be extremely old news, but in one full circle, that is one revolution or rotation, there are 360 degrees. Why? Because ancient mathematicians and astronomers approximated that it took the sun about 360 days in order to go around the Earth. Of course, they were not quite right about either of those things, but it still stands. If we have 1/4 of a revolution, that would be 1/4 of 360, which would be 90 degrees. For radians, you're simply describing in terms of the radius of the circular path. The nice thing about using radians is that if you travel this much along the circle at this point, let's say that this is Venus's orbit. Venus's orbit has a smaller radius than Earth's, and you can use this to kind of set up proportional stuff. But anyhow, one circle in radians, well, how many radii does it take to make a complete circle? Of course, it takes 2 pi radii to make one complete circle, 2 pi r being the circumference of the circle. What then would 1/4 of a revolution be in radians? Well, we do the same thing we just did with degrees. You take one full circle, 2 pi, and divide it by 4. 2 pi divided by 4 radians. Nobody in their right mind would leave that unsimplified, so we will simplify it down to pi divided by 2 radians. Now, rads is just a way of abbreviating it. Some people write rad, some people would just leave it as r. The habit that I'm in is to write it as either rad or rads. You should say radian when you're reading it because it can get confusing. I'm pretty sure that rads are an imperial unit of radiation exposure, like the Savert or the Gray in the metric system. One of you in the class can comment on it and correct me if I'm wrong about that, but just to be safe, say radians when you write rads. Some practice ones. 1 revolution in radians. Well, we'll do it like a simple unit conversion. 1 revolution. There are 2 pi radians in 1 revolution. 2 pi radians. Okay, we'd already done that one. That's your simple warm-up one. 5 revolutions, a bit more interesting. 5 revolutions. Some stoichiometry kind of unit conversion stuff here. Revolutions cancels. We get 5 times 2 times pi. Should, of course, be 10 pi radians. If you want, you could even solve that. 10 times pi as 31.4. And finally, 50 radians into degrees. Now, this one is worth doing. This one's much more fun to chew on. Let's take 50 radians. Adjust here. 50 radians, and we've been doing this, so I'll keep it up. 1 revolution is 2 pi radians. And then there are 360 degrees in 1 revolution. Get rid of common units. That should be 50 times 360 divided by 2 pi. We get about 2,864 and some change degrees. I'm going to round that up. Nice. And again, this is probably reviewed for most of you who have had this before and calculated, traded, or whatever. All right. So let's talk about the quantities when we're talking about angular motion. For example, when we're talking about translational motion, one of the things with which we may be concerned is displacement, going from x initial to x final. With angular motion, we are also concerned about displacement. However, it's just going to be along a circle instead of along a line. Again, translational motion should be kind of like this from here to here. Whereas angular displacement, let's call this center point Q. A particle goes from an initial point here to an initial position, or final position here. And what changed? This. Okay, so if you are trying to calculate this, let's say that you know that it is 50 meters along this turn. Well, what is that in radians? Or if you knew the angle change in radians, perhaps you would want to convert it to meters for the tangential motion. Well, the formula to do that is really easy. If you think about it, radians are already a conversion factor. 1 radian is the amount of meters in the radius of the path. Think about that again, I'll repeat. 1 radian is the amount of meters per radius of the path. So if we think about it like that, meters per radius, so what would you need to do in order to turn that into just meters? Multiply it by the radius. Here, I'll show you. The distance would be radius times your angular displacement. That is the change in angle, capital delta, lowercase theta. So here we have the distance. Now notice we're calling it distance in meters because this is not a vector. Otherwise, we'd call this displacement as well. It's not a vector when we're talking about translational motion because it goes in two directions. A vector can only have one. R is the radius, which is also in meters. You could even think of it as meters per radian. And then your change in angle in radians. If you look at that, it's a really simple unit conversion. No different than what we were just doing a second ago with degrees and radians and revolutions. Okay. Just to add it onto my drawing here, this would be the distance. And here we have the change in angle. And if you see, your radius would be here. There's the three parts of this formula drawn out for you. That's easy and almost boring. So let's move on to something else. Angular velocity. Of course, if you can have angular displacement, and there is always time in this universe, so angular velocity must be an important quantity as well. Not only how far does it spin, but also how fast does it spin. In fact, way more often will you be concerned with the rate of speed rather than the angular displacement. So angular velocity is exactly what it sounds like, the rate of angular displacement over time, or the rate of change in angular position over time. Now, as a quick reminder, translational or linear velocity is old reliable, probably the first physics formula you ever learned in your life. Velocity, displacement per time. For angular velocity, well, we can't use any of those letters. Oh, I guess we can use time because they're taken. So what we'll do is we'll use Greek equivalents. As you guys know, I'm enamored of the Greek alphabet. There is no V in the Greek alphabet. Interesting anthropological, or am I pronouncing that right? Forensics, in other words, looking at the face structure of old dead people. Apparently V is a pretty recent change in human vocabulary because the structure of the mouth, I think it was the lips and tongue, have changed over time. So a lot of old languages did not have V in them. The closest thing we have is omega, of course, capital omega, already taken by resistance. Not that that's going to be on this year's AP exam. So we will use a lowercase omega. For those of you who do not know, it looks like this. Kind of somewhere between a W and a but. So angular velocity omega is equal to the change in angle, that is your angular displacement, over time. Exactly what you thought it would be. Angular displacement over time, translational displacement over time. Same formula, just new letters. In terms of what the units will be for this, remember we're worried more about radians at the moment. So this would be in radians per second. This would be in radians. This would be in seconds. think it's worth considering, what if something spins in a full circle and that's the data you have to work with? Or if you are given the amount of displacement, not in radians, but in revolutions, well, then that implies a full circle. So if you're given something in revolutions, an interesting thing that you can do with that is find the period per revolution using this formula. There we go. Just rewriting it. And then we look back to the formula we have right here. We know that the change in angle is distance per radius. Okay. So let's plug that in place of the delta theta. We would get distance divided by radius and also time. We are most of the way there to creating a new interesting formula. Remember, we're talking about if they gave you something in revolutions per minute or revolutions per second or revolutions per year or whatever. Revolution is a complete circle. The distance around a complete circle is 2 pi r. When we plug that in, we get the final useful transformation of this. 2 pi r, but we have an r on the bottom, so it'll cancel, over t. But this t now describes the time taken to go in the circle. Of course, if it's period, we should capitalize it because it's the full period. Any repeating amount of time is given a t. So if we have in full circles 2 pi over t, kind of interesting that radius cancels out there. But if you think about it, radius should cancel out. Imagine a turntable. And on that turntable sit 2 ladybugs, one very near the edge of the disc, the other one closer to the center. They make very different circles, but they both make circles. Which one wins the race? Of course, they would get back to the same position that they started at in the same amount of time. And thus, radius should not matter if we're only concerned with 2 different full circles with the same angular velocity. Kind of neat. If you have one of these and would like the other, that is, if you have translational and want angular, or you have angular and want translational, of course, that would be a tangential velocity if you convert it. Tangential velocity is equal to radius times angular velocity. So you just, again, use that radius as a conversion factor. It's meters per radian. This is radians per second. Radians on the top and bottom cancel, giving you meters per second. Or if you are a visual person and would like to follow that this way. Now, so this allows you to convert your tangential velocity to angular velocity. Let's take an example. If you were given 23 revolutions per minute, question of concern 1. What is the angular velocity in radians per second? I'll leave that as an exercise for the viewer for now. Question 2. What is the tangential velocity Of course, in order to know that, we would need a radius, so let's make one up. 5 meters. Now that we have that, what is the angular displacement over, of course, if you look at this, we want to find angular displacement, we would need a time. So call it 2 seconds. And lastly, not leastly, how far does a ladybug on the edge This is one of those robot calls. I'm going to lose my mind. It is. I can't even escape them teaching from home. They call every day during 5th period. How far does a ladybug on the edge rotate in 2 seconds? Strongly recommend pause the video, work these out, and then hit play when you are ready to confirm or deny your work. Of course, you do that on your own. I'm just going to keep writing. All right. To convert 23 revolutions per minute to radians per second is trivial. 23 radians per minute. In 1 minute, there are 60 seconds. And I realize I screwed that up there. And in 1 revolution, there are 2 pi radians. Get rid of common units. We'll definitely get an answer in radians per second, which is good because that's of course what we want. 23 times 2 would be 46 pi divided by 60. And that's, of course, in radians per second. Simplify should be 2.3 and some change. Let's call it 2.4 radians per second. What's the tangential velocity if we have a radius of 5 meters? Well, tangential velocity we can find using our angular velocity we just found. Just radius times angular velocity. So plug in 5 meters per radian times 2.4 radians per second. 5 times 2.4 should be 12 meters per second. What is the angular displacement over 2 seconds? Well, angular displacement we could find if we knew the tangential displacement. We don't. Or that is to say the distance traveled, and we don't know that either. Or we could take something we do know, that is the angular velocity, and we can find the angular displacement of that. As usual, you're just picking and choosing the formula to use based on what do you have to work with. All right, so we have to work with omega equals delta theta per time. We want angular displacement, so move the time over to the other side. Cross multiply. And it's going to be 2.4 radians per second times 2 seconds. And again, we get something trivial to do. 2.4 times 2 is going to be 4.8 radians. Seconds being on the top and bottom cancels. How far does a ladybug on the edge of the turntable rotate in 2 seconds? You could start this from the tangential velocity, do it that way, use old reliable, or you could do it with the fancy new stuff like converting angular displacement into translational. I'll show both ways. If we use velocity as a displacement over time, 12 meters per second times 2 seconds. Obviously, the ladybug goes 24 meters. If we use distance is angular displacement times radius, then it'll be 5 meters times 4.8 radians, which is what we just found for 2 seconds. They had different times. You could do it again as more steps. But 5 times 4.8 also gives you 24. When there are multiple methods, you should feel relieved because you only have to remember one in order to be successful. All right, think about this for a moment. You're turning and you floor it. Now we know from our centripetal motion unit, that's a bad idea because your speed is one of the things that determines how much force is required to keep you in the turn rather than skidding out of it. But let's say you've got really, really soft, grippy tires. You're turning and you floor it. What happens to your rate of turn? Well, presumably you go faster. So if we can have angular displacement and we can have angular velocity, we should be able to have angular acceleration. Now this is something that we mostly ignored in order to do centripetal force as easily as is possible. They were turning at the same rate, which gave them a centripetal acceleration, but that didn't change the rate at which they turned. We assumed a constant angular velocity for every single one of those problems. But Kepler taught us, for example, the Earth changes its rate of revolution as it goes around. When we're closer to the sun, gravity pulls us toward the center more, and we speed up. When we are farther away from the sun, we will slow down just a little bit, and we'll have angular deceleration in our rate of revolution. So, angular acceleration would be the rate of change in angular velocity. For translational, acceleration is simply the change in velocity over time. V final minus V initial if you want to write delta out. For angular acceleration, it's exactly what you think it is. Of course, A for acceleration is already taken by the linear acceleration. So we have to go to the Greek alphabet again. The Greek alphabet equivalent of A is alpha. Capital alpha looks the same as capital A, so let's ignore that one and use a lowercase alpha. Looks like this. Not terribly different from a regular A. Change in angular velocity omega over time. you had this and wanted to figure out what that translates to in the change to your centripetal acceleration, again, you simply use the radius as a conversion factor. This would be in radians per second, and this would be seconds, thus this is radians per square second. This is in meters per radian. Radians cancel, giving you meters per square second, which is what we're used to thinking of acceleration in terms of. All right. With that, you should be equipped to try the practice sheet that I have posted. Give those a look-see. And also, we'll meet up in a couple days on Zoom in order to fill that out if you're having any trouble. These quantities work with all the same kinematic formulae that we know and love. Let's see if I can kick it from the dome here and remember one of them. Displacement would be VIT plus 1/2 acceleration times squared. All you have to do to make this apply to angular motion is substitute. Delta X, change in position, well, we're more concerned with the change in angle, angular displacement. Really, you're just going by and putting the word angular in front of it. Angular displacement is angular initial velocity. You don't have to put the word angular in front of time. There's no such thing as angular time yet. But when we get a second time dimension, I'll get back to you. 1/2 angular velocity alpha times squared. It really is that simple. Just substitute the letters. And if you want to get the values to go back and forth as opposed to just the formula, then all you have to do is multiply by the radius to turn one into the other, or divide by the radius, I guess, if you're starting with the tangential. All right, get to work.